After talking about the system level of SerDes, let's dive into the critical block of the clock generation, which is a fixed loop PL. There are so many topologies of PL, and let's go through the two fundamentals PL first. We'll show the image of why the Type 2 PL is more popular than the Type 1 PL nowadays. The PL has a few applications images as follows. First, frequency synthesis. For example, multiplying a 100 MHz reference clock to 8 GHz for PCIe 3 8 gigabit per second application, if that's a full-rate clocking. Second, deskew or skew cancellation. For example, phase aligning an internal clock to a big clock tree or any I/O clock. Third, clock recovery or clock data recovery CDR, which we discussed extensively before. Fourth, modulation, demodulation. For example, Gaussian frequency shift keying GFSK in a Bluetooth low energy wireless system, or spread spectrum clocking in a EMI reduction wireline system. So, what's the PL images inside? The fundamental operation of the PL is the same among the mentioned applications as follows. First, the phase detector PD measures the phase error between the feedback clock and the reference clock. The loop filter then filters the phase detector output, thus generating the VCO's control voltage VC. If the phase of the VCO is late, the VC will increase to speed up the VCO's frequency. Since the phase is the integral of the frequency, the VCO's phase will be earlier to make the divider's output phase earlier, and vice versa. Therefore, the PL in a steady state should maintain frequency lock to a reference signal by this negative feedback system. From this traditional and simple PL, we can define the PL type, which refers to the number of integrators within the loop. As we mentioned, the phase is an integral of the frequency of the VCO. Any PL is always at least type 1 because of the VCO integrator. Also, we can also define the PL order, which refers to the number of poles in the closed loop transfer function. So, the order can never be less than the type. Let's start with a simple type 1 PL image. Here, we take the type 1 PL, only one integrator with a low-pass filter as a second order as a case study. What's the simplest low-pass filter? Correct. An RC filter would be the simplest one. But why do we need it? Correct. During the dynamic correction, the ripple at the VCO's control voltage will result in a big disturbance and deterministic jitter. Therefore, we like to make the control voltage VC as little ripple as possible. But we still have a phase error issue, even adding the low-pass filter. Think about the DC loop gain image for 5 seconds. Right, the type 1 PL may have a phase error if there is an input frequency step. Without looking at any equation, we can link to a feedback amplifier image we learned from Microelectronics 101. The output voltage error in the feedback loop depends on the open loop gain of the OTA. Ideally, if the OTA gain is infinity at DC, exactly follow the DC output voltage of the input. if the OTA gain is smaller, then the voltage error between the output and input is bigger, which is applied to any feedback amplifier configuration, or even the phase domain feedback loop in a PLL. Therefore, if we decrease the finite feed-forward DC gain for tracking an input frequency step, then the phase error between the feedback clock and reference clock is increased. Alright, what's the bandwidth issue related to the DC feed-forward gain? Yes, to have a low phase error, we may need to have a larger feed-forward gain, which leads to a wider bandwidth. Unfortunately, in some applications, instead, we would like to have a narrow bandwidth to filter out the input reference clock phase noise or jitter. So again, the type 1 PL is out. Before realizing a better type of PL, what's the PL capture range here? Think about the phase detector image for 5 seconds. Bingo! An ideal phase detector PD only has limited capture range 2 pi, which is not enough if there's a frequency offset before steady-state lock state. What can we do? Or what do we want? Correct. We want to extend the range with a constant slope and polarity asymmetric about 0 phase to achieve the wide frequency range operation as shown here, with a simple phase frequency detector PFD through 2 reset flip-flops and 1 AND gate here. Okay, we improve the capture range. How about the phase offset? In another perspective, how to increase the DC gain for tracking an input frequency step? Think about the integrator image for 5 seconds. Right, by adding the extra integrator, even though the frequency step at the input will have a 0 steady-state phase error, you can prove it by yourself from the final value theory. So, what's the simplest integrator? Yes, current dumped to a single capacitance as shown here. Now, do you see any extra issue with a 2 integrator? Correct. The 180 phase shift will cause the PL to become positive feedback and offset. Therefore, a simple frequency compensation is needed by adding an extra 0, which is another R1 in series with the C1. Unfortunately, the R1 will cause the voltage ripple and spur we don't want. Therefore, the capacitor C2 is often added for additional filtering to reduce the reference spur. Here are the summarized images of why the Type 2 PL is more popular than the Type 1 PL nowadays. There are so many topologies of PL, but the fundamental type of PL is the same. First, the steady-state phase error still exists in Type 1 PL if there's a frequency step at the input. Second, we can maximize the loop gain to reduce the phase error between the reference and feedback clock. But we must increase the Type 1 PL bandwidth, which may increase the reference phase noise contribution, and is sometimes not preferable from a poor reference clock. Lastly, the capture range through the PD is narrow and cannot pull in the frequency error effectively. Therefore, a phase frequency detector PFD with a constant slope and polarity asymmetry about the zero phase difference can extend the wide frequency pooling range. Also, the PFD output can match the following integrator with a charge pump to a capacitor C1 properly to realize a type 2 PL and eliminate the issue or design constraints from the type 1 PL. But a simple frequency compensation is needed by adding an extra zero through another R1 in series with the C1. Not yet. The capacitor C2 is often added for additional filtering to reduce the reference spread from the R1. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and please share your comments down below. Lastly, please share the video link with the people who may be benefiting from it.